so let's talk about final exam, which I've mostly written at this point. Well, let me go to Canvas and see if that's the proper one.
I hope Canvas has the answer sheet.
That would be awesome, right?
Little do I know, the answer sheet's all up here.
Yeah, exactly. Final exam study guide, subject to change, of course. All right. So there's probably some things on here that we did not go over, like the stuff with pulse width modulation. So I'm going to do this the right way. So basic things you can expect to see on the exam. Writing snippets of code. Okay, so seeing something like if x is greater than y, then z equals x plus 2. Alright, so I might say here's a C statement. Lost myself. So here's a C statement. Go ahead and write some pick code that does this, right? And so you take x and you subtract y, and you check to see if the result's negative, or you do a compare file and skip if less than or something. And if x is bigger than y, you take x and you move it into w, and you add LW2 and you move that into z, right? Or however you choose to do it. There's always multiple ways to do it. But you're really just writing, you know, a few lines of code that correspond to this. And don't do things like done go to done, or branch up to the top, or enter infinite loops, or things like that. Just you know, a few lines to correspond to that C. Don't set up interrupts and add con1 and include files and all that kind of stuff, right? If you're in doubt, come up and ask, hey, do we need to show such and such? And I'll say, yeah, you got to set up the I/O system or whatever. But try to sort of just do the bare minimum, because you want to have time for this stuff. So you'll see questions like that. You'll see questions related to input and output. Okay, so tris say port B, add con1, that sort of stuff. You'll see questions related to interrupts. So writing some interrupt code to do things in response to certain interrupts. So having to set up the interrupt system, the intcon registers, the PIR register, putting code at location 8 or 18, putting code in the beginning that branches to some main section, all that stuff that we've done every time we've dealt with interrupts. You'll definitely see questions on the timers. So you want to know how to set up the timer configuration registers like T0 con, okay, for the prescaler, for do I want 8-bit or 16-bit and so on. And you want to know how to figure out what those settings should be for a given time interval. So if you want a 1-second delay and you know you've got 8,000 instructions per second, you need to wait for 8,000 ticks. If your prescaler is 1-to-1 and you're 16 bits, start at 65,536 minus 8,000. If you're using a prescaler of 2-to-1, then you only need to wait for if you're using a prescaler of 2-to-1, then every other instruction tick is going to increment your counter. So you'd only have to wait for 4,000 increments. And so you could start at 65,536 minus 4,000. If you make your prescaler big enough, you may only need to wait for 50 increments, in which case you could use an 8-bit timer, initialized 206, and then after 50 increments it overflows, and so on. So all those details, right? So you'll have some questions related to that. You'll have a question that uses indirect registers. So similar to the homework that you just got back. So dealing with FSR 0, 1, or 2, high and low, and dealing with INDF 0, 1, or 2, or post-inc or pre-dec or whatever you choose. What else? That's what comes to mind right now. So let's go through this. All right, so binary numbers, hex, decimal, twos, complement. We've done that stuff. I'm not going to give you a page of convert these numbers from binary to integers and so on. Oh, floating point, that's another question you'll definitely see. So floating point, similar to what you did on the board, either going from floating point to hex or going from hex to floating point or both. All right, so basic binary stuff, including numbers that are smaller than 1. So how do we convert 0.375 into binary? So multiply by 2, take the thing on the other side of the decimal point, and so on. RISC versus CISC, we've been dealing with a RISC processor, a reduced instruction set. That's why it takes so many instructions to do simple things. A complex instruction set machine, you could multiply 2 floating point numbers by just saying fmul. There'd be an instruction maybe that would say, give me 2 floating point numbers, I'll multiply them for you. On a PIC, if you want to do that, you got to do all those things we were talking about before the break. Right, so that's a complex instruction set versus reduced. PIC memory organization, we have data memory and a program memory. They're separate things. Okay, that's classic in RISC systems, because RISC machines try to run at a very high clock rate, because you got to do a million things to do anything useful, right? Don't worry about the bank select register. But worry about the access bank. Okay, so this access bit that we set to a 1 or a 0 to say what 12-bit address do we really want to access? Are we accessing a 12-bit address that begins with 0000 or begins with 1111? Right, because we can only specify 8 bits, and so if we want to access F80, we've got to somehow say, hey, the first 4 bits of that 12-bit number should be 1. We use the access bit for that. Special function registers, those are the registers that begin with an F in that first digit, so F80 through FFF. Those are file registers like any other, except they have particular functions, usually for dealing with hardware or things like WReg. And so we use special function registers to interact with the PIC subsystems like the timers, the interrupts, the input-output subsystem, and so on and so forth. Coding of assembly language instructions into binary, I'm probably not going to ask you to do that, because we did that on the midterm, and I'm comfortable everybody knows how to do that. But it's a good thing to keep in mind, right, because it lets you know what you can and can't do in your instructions. But you should know that pieces opcode is what you want to do, operand is what you're doing it to. Destination bit says, should we put the result back into the file register we're working with, or should we put the result into the W register? 0 means W, 1 means the file register. Access bit we talked about. Literal values, remember, is an 8-bit value that we're actually just going to use that 8-bit value as is. If we move LW17, it puts 17 into the W register. If we move F17, 0, it puts the contents of file register 17 into the W register. Right? Most of these instructions deal with the contents of a file register. A literal says 17 is not the number of a file register, it's just a 17. Put a 17 into W. Multiply by 17, something like that. And then converting from binary into assembly language is just hunt and peck on the sheet and find the bit patterns that match and go in the opposite direction. I'm probably not going to ask you to do that on here either. So assembly language instructions, right? Move F moves a file register to itself or to W. So mostly we use move F to go from a file register to the W register. Move WF goes from the W register to a file register. So they complement each other. Add WF adds the W register with a file register. Inclusive OR WF does an inclusive OR of a file register and a W register. And most of those we can choose where do we put the result. We want to go back in W or into the file register. That's the destination bit again. So comma 0 says the destination is W reg. Literal operations we just talked about. Bit operations take 2 arguments. So bit set file needs a file register and then a bit number. Bit number can be from 0 to 7. 0 is the least significant bit, so we can say bit set, bit clear, or bit toggle. And it will set the bit to 0, 1, or it'll set it to its opposite value. And so those are useful, bit set, bit clear, in particular when we're setting up interrupts. Right, so let's say we want to turn on int 0if in the intcon register. We could just say bit set file register, name of the file register, and then comma and the bit we want to set. Well, we could put a 1 because that's bit 1, but we could also say int 0if, and that's been set equal to the value 1. So this says go to the intcon register and set this bit. That'll put a 1 right here. Now we just turned on the interrupt flag. Usually we want to clear it, but just an example. So we've got bit operations. We've talked about bit masks. So if you want to work with a piece of a number, it's useful sometimes to take the other pieces of it and turn them into zeros, typically. So let's say we have a system where we want to know is port A bits 1 through 0 equal to 0. Alright, so port A bracket 1:0 is a shorthand for if I take bit 1 and 0 and treat that as a 2-bit number, right? Is this equal to 0? So port A looks like this. Right, it's an 8-bit value. There's 6 bits up here that we don't know anything about, but there's 2 bits down here, bit 1 and bit 0, and we want to know if those are equal to 0. Well, if we just say is port A equal to 0, it's possible that these are 0 and these things over here are not. So if we say is port A equal to 0, it might say no, it's not. But in fact, these 2 bits might be 0. So rather than check port A, we could do something like move F port A comma 0. And then we could AND it with this binary number 3. And now port A.
Can we turn off these lights?
Yeah. Thanks. Now port A looks like this. All right, because anytime we AND with a 0, it doesn't matter if this question mark was a 1 or a 0. When we AND with a 0, it's going to become a 0. So now, sorry, this isn't port A, this is W reg. So now W reg is a bunch of zeros followed by RA1, RA0. Now I can say is W reg equal to 0. And it'll be equal to 0 precisely if RA1 and RA0 are both 0. And the other values in these upper bits in port A don't bother me at this point. Right, so I'm masking out these bits so I can just look at those bits I'm interested in.
And we would just compare?
So at this point I could just say branch of 0 because AND LW sets the 0 bit.
B and Z, okay.
So I could say BZ, yes, and yes would be where I go if port A 1 through 0 was 0. So that's basic bit masks. And you can do AND ANDs to force things to zeros, you can do ORs to force things to ones, you can do XORs to toggle things. Okay, so we can do clear, set, and toggle with bit mask. And that ties into conditional instructions. So branches just jump to a location pretty close to us. Go-tos will branch to a location anywhere in program memory. Conditional branches, branch if 0, branch if carry, branch if not 0, will branch based on the current value of the status bits. So most instructions that we use will update status bits. So if I say add WF, it updates 5 status bits, carry, decimal carry, 0, overflow, and negative. If we do a compare file and skip if equal, it updates no status bits. So when we say BZ, we're checking the 0 bit based on whatever its current value is, which might be the previous instruction, it might be the instruction that executed 3 instructions before, right? Whatever the last instruction was that affected the Z bit, it's the result of that instruction that we're checking to see if it's 0. So you can do these conditional branches BZ, and typically we do something like move the file register, count into itself. That updates the 0 bits. Now we can say branch of 0. That's how we say branch of count equals 0.
So BZ is based on the Z register.
It's based on the Z bit and the status register.
And that's always based on whatever's on top of the stack.
It's based on whatever the last instruction was that affected the Z bit.
Oh, okay, so that could have been, like you said, could have been like 3 instructions.
Could have been 3 instructions before, right? Like a no op doesn't affect the status. So if I increment a file register and then I do 25 no ops, then I say BZ, it's checking the 0 bit as a result of that increment.
And that's whatever instruction is like.
Yeah.
1 minus 0. Yeah, okay.
Yeah.
1 minus 1 would be it.
Yeah, if I did 1 minus 1, then the 0 bit would be set.
Okay.
So then if I did BZ, it would branch.
Okay.
So it's the pick version of doing an if-then. It's really an if-then go-to. We don't teach go-tos in C, but that's basically what it's doing. All right, there's these skip instructions: increment file and skip if 0, decrement file and skip if 0, test file and skip if 0, and so on. I will not ask you to use these. If you want to use them, feel free. So a bunch of people use them on the homework, and this time most people got them correct. So that's good progress. So if you like these, right, stick with them. But I won't force you to. So you can always do a conditional branch, or you can do a skip. It's your choice. All right, calls and returns. Basic behavior. Call is just like a go-to, except it saves your return address on the stack. The return says, look at the address that's on the stack and go to that, but also pop it off the stack.
Are we going to need to know that for the final?
I think we did those on the midterm. So yeah, you need to know them because you might have to use them, but I'm not going to give you a sheet of, here's the stack, show me what happens when you do calls and returns.
Okay.
But you definitely want to know how to use them because you use them, and it's the same mechanism that interrupts use.
Okay.
An interrupt is basically a call to location 8, and a rec is basically a return. All right, so there's a stack pointer which tells you basically how many things are on the stack, and there's 3 registers that show you the value on the top of the stack. Top of stack, upper, high, and low. If you push too many things, you get an overflow. If you try to pop too many things, you get an underflow.
Are we going to be messing around with those registers on the exam? Or is it mostly using calls and returns?
Mostly using calls and returns.
Oh, okay.
Yeah. You can, so we know that when we get an interrupt, we do a call to location 8 or 18. We've talked about the shadow registers, right? So the W register and the status register and the bank selector saved in these holding areas when you get an interrupt. We can also use those when we do a call. We can say call something comma fast or comma 1, and it'll use those shadow registers. But they sometimes cause more trouble than they're worth, so we haven't really played with those much. But down the road, if you're doing big stuff, be aware that we can use the shadow registers ourselves too. All right, programming, coding algorithms into assembly language. We talked about that. That was the first thing. If then else statements, while statements, for loops, arithmetic expressions, things like that. So snippets of code. Also looking at assembly language code and trying to figure out what it does. So we have one of those on the midterm. But you know, when you write code, you'd like to be able to do that yourself. Write some code and then go through and look at the code and see if it does what you were hoping it would do. Because assembly language gives us very few errors. It just silently does the wrong thing. All right, input output. So port A, port B are for reading, latch A, latch B are for writing, tris A, tris B are for specifying whether we want to read or write from each bit. Set a bit to 1 to say you want to do input, set it to 0 to say you want to do output. RA5 is not pin 5 on the PIC processor, right? To know what pin RA5 is, you got to look at the data sheet. And if I look on here, RA5 is actually pin 4. So there's a mapping, and it just comes from the picture on the front of the blue data sheet summary. Interrupts. So I did this morning, but it's probably worth writing out once more. So interrupts, what do we want to do? You need to enable interrupts from a particular source. For example, if I want an interrupt from timer 0, I have to enable timer 0 interrupts. Okay, and this is typically the IF, int 0 IF, AD IF, timer 0, sorry, interrupt enable IE. So enable your particular source of interrupts. Set priority. For example, int 1 IP. Not all interrupts have a priority option. Int 0 is always high priority. But you can set the priority here. There may be other options. So for example, interrupt 2 has an edge option. So we can say, do we want to interrupt on the rising or the falling edge? So like int edge 2. So enable it, set the priority, then it's probably a good idea to clear the flag. So those are just examples, depending on what the interrupt is. And you want to do one of those batches of things for each thing that you want to have cause an interrupt. So if you're using int 0, int 1, and int 2, you're going to do this thing 3 times, right? And you can do it multiple things at once, or you can, you know, set up int 0, set up int 1, set up int 2. All right, and then you want to enable priority levels. So that's just bit 8 in the Archon register, bit 7, most significant bit. So bit IPEN. I'm up here under other options. For example, if you're dealing with interrupt pins like int 0, int 1, int 2, you want to set the corresponding bit in the tri-state B register to say that pin is an input, and you want to set ADCON to 7F, say digital input, and so on. So that you got to know the details of your interrupt source. All right, so do that per source, and then enable priority levels. And then last thing you want to do is enable global interrupts. And that's the global interrupt enable high and low bits in the INTCON register. All right, in your program memory, location 0, that's your reset vector. That's where your code begins. Doesn't matter what you write, doesn't matter how you say org, doesn't matter if you have interrupts. When you power on your processor, it's going to start with instruction 0. If you haven't put something there, it's a gamble what's going to happen. All right, location 8, that's your high priority interrupt. When a high priority interrupt occurs, you're going to execute whatever instruction is stored at location 8. In location 18, that's what's going to get executed whenever there's a low priority interrupt. And this program memory map, that's all that's forced on you by the architecture. What you do with that is totally up to you. You can write your whole program starting at location 0, and you can step over locations 8 and 18. And as long as you're not using interrupts, that's perfectly fine. You can take your interrupt routine for a high priority interrupt, and you can put it right here at location 8 if it's really small, or if you're not using low priority interrupts. You can step over location 18. It's totally up to you. Okay, you have absolute control over this. The only thing that's mandated is when the processor starts up or resets, going to execute the instruction at 0. If it gets a high priority interrupt, it'll execute 8. If it's a low priority, it'll execute 18. And you get to do what you like with those. Okay, and then the last piece of this is inside your interrupt code. You generally want to clear the interrupt flag. Otherwise, when you exit, you'll get another interrupt because the interrupts are triggered by that interrupt flag. So clear the interrupt flag. Do stuff. And then return from interrupt with enable, so retv. Up here in the beginning, you may need to decide who interrupted. So if you have 6 different things that could generate interrupts, if you enabled 6 different sources of interrupts, and they're all high priority, if any of them interrupts, you're going to jump down to location 8. And whatever code you start executing there, it's not going to know what caused the interrupt. It's going to know something requested an interrupt, but it could be A, B, C, D, E, or F. So generally you have to go through and you have to start looking at the interrupt flags to figure out what caused the interrupt. And then decide what to do. And sometimes, in the very beginning we want to save stuff, and at the very end we want to restore stuff. So if your main program is just a loop that says, you know, loop, go to loop, we don't really care if our interrupt code changes the W register or the status bits or things like that. But if your main program is doing a bunch of stuff and it's using the W register and the status bits and file register 18 and all this other stuff, anything that you change in the interrupt routine, you got to change back before you exit, including the W register, including the 0 bit, all that stuff. So if your general code is doing stuff, you need to save things in the beginning and then restore them at the end. Yeah?
So is that usually if you have multiple interrupts that could possibly happen? Because otherwise you can do retv1, right? And do the shadow register.
If you're only concerned with WREG status and bank select, yeah, you can do a retv1 and that'll work great.
Like a counter
but if you had a counter, or classic case in the lab, you're using a delay routine, and you try to use that in your interrupt routine, well, that changes the value of those counts. And when you go back from the interrupt, your program is not in the same state it was. And so it takes 53 seconds for the LED to change again after that. All right, so save stuff. So that's a general prescription for interrupts. All right, so what happens when you do an interrupt? So the other thing is interrupts of the same or lower priority level are disabled. So if we get a low priority interrupt, once we're in our interrupt code, low priority interrupts are automatically disabled for us. So any other low priority interrupt will not be honored until we do our retv. But if we're in our interrupt code and we get a high priority interrupt, that will interrupt us. So we're at location 18, we're executing our low priority code. Someone hits int 0 and that's been enabled, boom, we jump back to location 8. And now we're doing our high priority code. When we say retv, we're going to come back to the middle of our low priority code where we were, finish that up, and when we do that retv, we'll go back to the main program. So these things can nest. Big machines might have 30 different priority levels available. And so you can get all kinds of interesting dynamics.
Can we just like brush up on indirect referencing?
Yeah, yeah.
Just like give us some examples of like how to use and not to use.
I'm going to take out this section on PWM. All right, let's talk about indirect addressing. So if you're comfortable with the language of pointers, INDF0 is just star FSR0. It's the thing that FSR0 points to.
It's a file register, right?
It's a file register, but it's not a physical one.
INDF0 is.
Yeah.
Okay.
So suppose FSR0, and again, this is FSR0 high appended with FSR0 low. It's a 16-bit register. I'm just calling it FSR0. Suppose FSR0 is equal to 1. If I were to move INDF0 into W, what value would get moved into W?
Whatever 1 is holding.
Which is 15. All right, so we're going to do move F INDF 0, comma 0, put into the W register. So if FSR0 is a 1, INDF 0 is not the value 1. Okay, it's the contents of file register 1. If FSR0 is a 4,
16.
it's 16. It's the value of file register 4. You got it. That's all there is to this. Okay, so it's just a level of indirection. Now, if you want to get fancier, suppose FSR0 is a 2, and I do something with postinc 0. I move postinc 0 to W. Okay, postinc 0 is not 2, it's the contents of file register 2, which is 11. But after that happens, FSR0 gets incremented.
So 11 still stays there, but we move to...
So this was 11, we could have copied into W, or we could have said, add 1 to it or something. But after we're done with this, FSR0 actually changes also, it gets incremented.
Oh, okay.
You can live without that. It's just useful because a lot of times we're trying to access registers one after the other. And if we use INDF0, then we need to increment FSR0 to 1, use INDF0, increment FSR0 to 2, and so on. If we use postinc, it says automatically increment FSR0 after we're done with it. But you can live without it. It's really fun if you set up FSR0 to point to itself and then try to use postinc or something like that. They tell you in the data sheet somewhere not to do that. So there's variations, there's postinc, I always forget what the options are. There's a postinc, there's a postdec, and there's a preinc. So the post one's increment or decrement FSR after you do your operation. The pre does it before. And then there's plus W0. I won't ask you about plus W0, but plus W0 basically let's say FSR0 is equal to 2. Plus W0 is not 2. It's also not the contents of file register 2. It's the contents of whatever file register is 2 plus W. Right? So if W equals 3, this would say take FSR0 as 2, W is 3, add those together, 5. This is the contents of file register 5. So it's star FSR0 plus W reg. And you can live without that too, but it's a lot more convenient to have this. Does that help?
Yeah.
And you can play with these, you can play with the heck of these in the simulator.
Okay.
And get a bunch of practice. And the simulator's totally solid for this.
If we were to check like what INDF is equal to, you would give us a number which corresponds to the file register it's looking at.
Which file register?
The most recent one.
Not exactly. This is the trick. So INDF0 gives us the contents of a file register, but which file register?
FSR.
It's the file register whose number is in FSR.
Right.
Right.
Which we set.
Which we set. So put 17 into FSR, INDF0 is the contents of file register 17.
And then we could just use that for as a counter and then scroll select up and down. You do that. Okay.
Yep. If this is fuzzy, right?
But we would use that using INDF0.
Yeah.
To view. Okay.
If this is fuzzy, definitely go into MPLAB and write some code, right, and see what this does. Just, things like what I've done here, give FSR a value, load some values into the first few file registers, play around with FSR0 and INDF0. Questions about timers? We've talked about these in multiple contexts. We spent a lot of time on it this morning before class.
What's AD conversion?
That comes next. Analog, that's the analog input system.
Is that gonna be in the final?
Maybe.
Okay.
We'll talk about it in a minute.
Alright.
But questions about timers? System clock is 32,000 divided by 4, you get 8,000. That's how many instructions happen a second. So an instruction is an 8,000th of a second. If you don't set any funny prescalers or anything, basically every instruction your timer 0 register increments. And when it overflows, it requests an interrupt. That's the whole timer subsystem. The details are, when does it increment? Well, normally it increments every instruction, but if you put on a prescaler, it may increment every other instruction, or every 4th instruction, or every 8th instruction. If it's only incrementing every 8th instruction, it increments more slowly, it takes more time to overflow. So we get a longer time before the interrupt request with a bigger prescaler. And does it overflow at 256 or at 65,536? That's the question of using 8-bit versus 16-bit. So you take all of that and you can generate a certain delay until an interrupt happens by loading an initial value into timer 0, high and low. The closer you start it to the overflow point, the sooner it's going to overflow. If you start those timer registers at 0, it's going to take a long time till it overflows. If you start them really close to the largest value that they can store, it's going to overflow very quickly. So you can adjust your timing till an interrupt happens by tweaking those parameters. How many bits, what the prescaler is, and what the initial value is. And then timer 2 is just weird, right? Timer 2 is different because instead of overflowing at the largest value, it basically overflows whenever timer 2 is equal to PR2. So if you set PR2 to 10, it'll count from 0 to 10, request an interrupt, go back to 0. Count up to 10, request an interrupt, go back to 0. So that one's different. Everything else counts from its current value up to, say, 65,536, request an interrupt, goes back to 0. And we've always used the internal clock, but we can drive these things with external clocks also. There's pins you can pick on here. I believe oscillator 1 and oscillator 2, but there could be other ones. Maybe T0 clock in, that you can use to say, hey, I want, instead of using the instruction cycles as the source of my clock, I want to feed in something from the outside. And now I take a 555 and have it generate a pulse every second, and now, you know, same thing, but instead of an 8,000th of a second, it's 1 second. And every second your timer register increments and so on. All right, A to D conversion. So this is the thing where we can feed an analog voltage into the chip and we can convert it to a digital number. And it's a, I was about to say 10, is it 10 or 12 bits? 10 bit, I knew that. So you feed it into one of the analog input pins, right, and these are labeled AN0, AN1, AN2. Right, and you set up your ADCON registers to say which pins do you want to use, which channel do you want to convert, all the stuff with how long do you want to do the conversion for, what's the conversion rate, and all those details we skipped over. Basic punchline, you turn on the go pin and it starts converting, and when it's done converting, that bit changes from a 1 to a 0. And when it's done converting, your result is in a pair of special function registers, AD result high and AD result low. And you can read those and do whatever you want with them. So you're using this in your sensor code. Right? You're taking the value coming in from the sensor and changing it into a digital number. And the larger that number, the further away something is. So you can look at the starting sensor code for Lab 6. To see a good example of A to D. Alright, types of questions, convert numbers, convert between assembly and binary, read an assembly language and analyze, including effects on registers and stack pointer, write short assembly language. Analysis of the behavior of a circuit. Yeah, we haven't talked about circuits in this, but you can build circuits with this chip. Alright, and you may have to do that. So, make sure you know how to hook up LEDs, you know how to hook up switches, you know that pin 4 goes through a resistor to 5 volts. You know the power supply goes directly to 5 volts, the ground goes directly to ground. And that's pretty much it for the hardware. It kind of always gets built the same way, and then if you want to use an input or an output, you just put on switches and LEDs. Short sections of code to interface with PIC ports, tri-state registers or other registers. PIC code snippets to implement C algorithms, PIC codes to work with timers. Work with timers or specify special function register contents. That sounds confusing. I'll just say etc. Write or analyze interrupt-based code, floating point conversion. Short answer conceptual questions about assembly, the PIC processor, I/O interrupts, memory organization, pulse width modulation, and so on. And indirect registers to implement code or analyze code using the indirect registers. I'm not planning any surprises on this. Okay, this should be very straightforward. It should be very similar to the things that you've been doing. I may take multiple concepts and have you use them in a problem. So you may do something that's doing some I/O and doing something with interrupts at the same time. Well, you had problems like that on the midterm, right? But I'm not planning any, I've never seen anything like this before kind of questions. Or I mentioned once for 5 seconds this thing, now here's a 20-point question on it, right? I'm not going to do that to you. So these should be pretty straightforward. Doesn't mean it's going to be easy, right? So if you're spending a lot of time, don't say, oh, he said this was straightforward, I must not get it. These things take time, okay, and they take work to do, but they should be things that you've done already and that you're familiar with. So it's an hour and 15-minute final. I don't want time to be an issue for people, so here's the deal. We're going to start probably about 12:15. So if there's questions that you've got to ask before the exam, right, we can talk about that for a few minutes. We give people time to trickle in. We'll start at 12:15, go nominally till 2:15. But if you need more time to work on it, I will let you have until 3:50. Okay? It's supposed to be a 2-hour exam. I'm going to shoot for a 2-hour exam. It's doable in 2 hours. But if you feel like you need extra time, you want to check your work, I don't want you to get time crunched because people got time crunched on the midterm. And I'm not really worried how quickly you can do this stuff. I want you to understand the concepts and demonstrate that. So it's a 2-hour exam, but if you need an extra hour, hour and a half, I'll be here and I'll hang out. Okay? And then if you still have lab work to do, you can use the lab afterwards, obviously. But I think most people will be done with their labs today. Any other questions, concerns?
What's the lab report do? Wednesday?
Yeah, Sunday morning at 11.
Oh, okay, so we wouldn't even need, because the final's on Tuesday.
Yeah, final's on Tuesday.
So we wouldn't have any lab time on Tuesday.
So no lab time on Tuesday unless you're doing something late or you just want to play or whatever. And then Thursday we'll probably spend the whole time in here. Orange juice and cookies and lecturing on stuff.
Are you going to be here early on the day of the final at all?
Wasn't planning to.
Oh, okay.
And you really don't want to be like conceptualizing stuff right before the exam.
So that might screw.
This was one of my like 5 rules when I was an undergrad. It was like never get to the class early, and if you do, don't hang around the pool of students who are like explaining concepts to each other because most of it's wrong.
Okay.
At that point, it's like panic and fear speaking. So you really want to kind of like do the panic and fear part ahead of time and figure it out.
Right now.
And then yeah.
When I panic and fear, I just fight people.
Yeah.
All right, let's do it.
Yeah. So do that and make your notes and go through homework problems, labs, and stuff like that. Working from your note sheet to make sure it's complete for what you need.
I'm gonna bring Krispy Kremes.
Yeah.
Okay.
That rocks.
I can bring bagels.
Okay.
Great. You better do it though.
All right, so I'll post the study guide. I'll post the videos from today. I don't know how the audio came out because I was up there most of the time. But
Wait, you made
I'll-
a video today?
yeah, I was recording these.
Oh no! I just
Yeah.
kidding.
All right, so I'll be in lab in a few minutes.
Thanks, Nick.
Yeah.
Thanks for doing that early this morning.
You're very welcome.
That was awesome.